let's see if this works. I don't think I have MP real defined here though. At the very least we'll need this, I suppose. Oh, already have that. You have to tell me, why do you always say this kind of stuff? Skater 3. I mean, I can't even read this. What is this? Did you type this? Okay, so what do I have to link with to get MPFR? No. What? These are doubles. That should become the same again, but these are Oh, right, I didn't change the number of bits. Yeah, I have to use a look at an example. I think that the -3 thing. Where is that? Don't see it. Oh yeah. Yes. Oh, not really, actually. I mean, this is now precise. Actually, even this is precise. No, what nonsense what I'm saying. This is the input string. It's just same as that. This is what it makes of it. It is really ridiculous. Vier 40 digits. So how many bits is that? That's the ln of 10 to the power 40 divided by the ln of 232 even. It's more than 128, like way more 128. Is that a coincidence? Yeah, no, okay. I guess I want to get rid of the fixed. Now it is good. So this becomes visibly not the same as that again because it doesn't fit in a double. And if you use 128 bits, it just fits well with the 38 position. Hi, Fat Man. Yeah, algorithm to find the roots of a cubic, yes. But I have already been working on this for a couple of months. So, not sure if you can catch up. Well, you could do research, I suppose, in the sense that I haven't found anything really. I mean, you would think that and the perfect algorithm already exists, right? But yeah, I couldn't find anything. I did find someone who works for a company that sells a mathematical module to clients, blah blah. And he wrote the code that calculates the roots of a cubic, which is part of that module. And what they used, I mean, you would say, well, that's professional company, blah blah, so that must be the best code. But he just used the Cardano formulas, and he gave me the code even eventually, and it's horrible. It's for certain cubics, it just completely misses the correct value, completely. So yeah, I don't think there's. Apparently, there doesn't exist a good, at the very least, open source uh, algorithm yet. But yeah, what I did is I solved it mathematically. So, in the sense that I decided I didn't want to use Cardano because that uses several cube roots and or complex numbers or cosine and stuff like that. So I think I figured something out that is faster, which is that uses uh, well, stuff that I figured out to guess the root initially very accurately. And then I just apply the Haley's method a few times. And it turns out that you get the full resolution of a double, or on average after 2 Haley iterations. Only 2. That's really not much, yeah? But it has to do with the fact that I start with a very good first guess already. However, the only 90% of my randomly generated cubics then have accurate roots. Really, I mean, maximum accurate. And some of them turned out to be very inaccurate. Very inaccurate, even. So I started to investigate that already, I don't know, a week ago. And there is just, yeah, certain special cases, as it were, where, yeah, I need a better algorithm. So now I have a program that just generates random cubics and then solves it, so calculates the roots, and then compares those roots with really correct roots, which I would just throw a lot of CPU against it, and then I have the canonical correct root. And then if they deviate too much, I draw a graph, and then I look at all those graphs, and then I just see why. That's a special case. You see the special case. And then it takes me about 2 days to find a formula to detect the special case. And I filter those out, so I don't draw those anymore. And then it turns out that there's still cubics left that are inaccurate, which are not of the special case that I found, but they are another special case, which it then also can recognize. So I filter those out again also after another 2 days of designing a formula that allows me to detect those. And then it turns out there are even more cubics. I mean, more and more rare. They're not, I only generate 1 million cubics now, and then now there's maybe a handful left that are inaccurate. And yeah, that's where I was. I wanted to investigate why the hell this one is inaccurate. Well, it's not one of the two types that I already discovered that are inaccurate with the algorithm that I already wrote. So you just have to, be patient and go along for the ride. And then I suppose it will become clear, but yeah, it costs time. So MP real is a multi-position real. I just set it to 256 bits. So that will allow me to get the precise values. And then it's easier to compare. So now I'm using the get roots, that is by function, which already works usually, well, pretty good in most cases, to get very close to the correct root. And then I just call this new function with the MP real coefficients of the cubic. To get the exact root. Now I still have to write this. It's an array of MP real. Just put it here temporarily. Okay, that's nonsense. So of course you have a maximum of 3 roots. No, there's just 1 root. It's not an array at all. The thing should return a single root. The guess, and then using the coefficients of the cubic, determine what the exact root is then. Something is wrong with YouTube. I get a rotating thing instead of a. For the rest, everything seems to work. Why? Yeah. Anyone else problems with YouTube? Oh, I'm asking that. Oh, no, it's back. Okay. Let's just use Newton Raphson for now. Might as well use 2, I think. Just copy this. It looks good. Yeah, like pretty much what I need. I think I'm using U here instead of X. Let's use U then. Previous U is 0. Previous U step 0. Do I even use step? Oh yeah, okay. Previous step, do blah 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 blah. This would be the calculation of the Q of U, so it's called Q for some reason here. So that is evaluation. Evaluate U. Yeah, this is a Haley, but I think maybe it's a simplified Haley. So I use Haley? No, why not? I just need all the derivatives. don't even need the speed. Derivative, double derivative. Step is something negative. Yeah, make it positive. As long as that is unequal 0 and it's unequal previous and unequal previous. Then we continue and then we print it. And I want to print U every time, so I could do that here, I guess. And then we don't do this. And I need a second derivative. Times, that's a single times U. Yep. Okay. Haley. I don't know Haley. Not from the top of my head. Haley's method. To negative this 2 times. Yeah, I was working with a half, right? So there's a 2, divide both you divide this by 2 and that by 2. That would be the same, of course. That would mean that you can replace the second derivative by half of the second derivative. That's what I did, because then we save multiplying by 2 twice. 3 times even? No, twice. So the half of the second derivative is, and then you can just divide this by 2. Which saves 1 multiplication even. So this is then that times the first derivative divided by the first derivative squared minus that times the half second derivative. That would be the Haley's method. Okay, now let's see if this does something useful. It's not printing much accuracy there. None at all. Oh, that is because I'm printing to the debug channel, which is an output string stream. So it does not have the default precision that I set on the standard cout. You set a position on sentence out, but the debug channel changes every time, so we have to do this again. Or specific, rather. You see what is really going on there. So I think this is the original, right? Just the double is being converted to a multi-position reel on this and this, and then after a single Haley step, we are there. And then we do another step just to discover that we were there already. But that's okay. That's impressively fast. But yeah, okay. It works like a charm there. So this is wrong, because it should have been H26. Do we have it possibly with all those, not just this, but even that? Oh, it's ridiculous. 256 bits. Was it S double or 2 double? I think 2 double. It was 2 double. It is 2 double. So you see that if you convert the precise value, or this is now correct, those digits, back to a double, then you get 789 instead of 827, which is what you already had. So the current code already found the absolute best double. Well, that's for an absolutely random cubic, which I just made up here on the command line. And there are cubics that do go wrong. So now we're going to test one of those. I found Discord. So let's try. This one. So I think I found this one, which is already really bad. And then we change it to... it's actually not really bad. It's almost the same. No, it's not. What? So the correct value, well, this is the correct value with insane precision. And this is the one that fits in the double. So even the 161 still fits in the double. And this 9 here is, well, it's not enough. This should have been a 2. No, wait a minute. Yeah, it should have been a 2. So the 9 is too much. But it's the best double that you can get in proximity of the exact value. And what my get roots returned was this. And the fun thing is that if 161 is the best, well, it did begin with 114, and then it went better, it's closer to 16. And then it went to 18. What? It doesn't even go back. So I think this is Newton-Raphson. Newton-Raphson is completely failing here. You know what? This is what I'm listening at. Sometimes you hear a fly. The end. Yeah, well, I think this is the explanation, I think, of why it is this imprecise. Because even though there is room for improvement within the double, it even diverges from the correct. It goes the wrong way even. But this is Newton-Raphson, so maybe. I think, well, I happen to know how this thing looks like. I think this is like a curve that is where the root is equal to the inflection point and the derivative is basically 0 in that point. So yeah, and then Newton-Raphson doesn't work. Maybe Haley is better with roots where the derivative is 0. Guess I could try that out. Okay. Yeah, I'm even doing it twice, you see. So the first time we got a little bit better, and the second time did not even get better anymore. and this is just this was what was printed, and this is the Newton-Raphson. Now these are not lambdas. Evaluate is simply a function of no, it doesn't even find it really. Okay, we'll just go to derivative. Derivative, symbolic, 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 blah, 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 blah. Cubic polynomial. And this is the cubic polynomial, yeah. So I have a evaluate here and a derivative, which just takes a value. And we also have the second derivative. But this one has already multiplied it with 2. So maybe I should explicitly add a half second derivative here. Oh boy. Or, yeah, why not? Or otherwise I have to access the coefficients and then do the calculation myself. You can just get the coefficients using that. Yeah, what do you think? It's kind of weird to inside the cubic polynomial to add a... Well, maybe it's not that weird because it's going to be called by another member function of the same class. So I'm going to add a half. And I think that multiplying by 2 is infinitely precise. You might drop off the least significant bit, but for the most part it's just, no, not even that. The exponent of a double is just the exponent of 2. So multiplying by 2 is just incrementing the exponent by 1, which is super fast. I don't need a double code here. I think I can just return 2 times half, and that will then be equally fast. I mean, even though, you know, it's just even if the 2 wasn't just an increment of the exponent, it will just inline this, and then we do we do a single multiplication here while I remove the multiplication here, and in both cases it is a multiplication by 2, and this one is more precise. Oh no, it's not more precise. The precision is the same, yeah, because it just differs in the exponent. So yeah, and in that sense I could also have not added this one and then just call this one and then divide it by 2 again. I'm not sure if the compiler is smart enough to see that if you multiply with a literal, which is a half, that it produces code that just decrements the exponent of the double. It's not that simple, I guess. You could get an underflow and all whatnot. It has to check for not a number and infinity and yeah. So what was it? Evaluate times the derivative divided by the square of the derivative. Yeah, I don't want to call that multiple times. Let's just introduce new stuff. Square. Okay, that worked already. Interesting empty lines. What is going on here? Expect that primary expression before double. Half second derivative was not declared. Why? Oh, right, yeah. That is called from where? Random cubex. I have to add a half second derivative here. It's a test code. Probably have to do that again in, I bet, number 2. Is YouTube still working? Because even my music starts to stutter. Using too much CPU for compilation. Think something went wrong. Half second derivative. Okay, and that is called from random QX40. So boring. Keep doing the same thing over and over. That didn't change anything. This is shocking. It's still going to 173 and then still going to 188 from here. How is that possible? That would be the case if the second derivative is 0, which it is, I think, because there was a root in the inflection point. Yeah, if you do have a look at so if the second derivative is 0, then this is 0, and you just have to polynomial divided by the derivative, because I calculated once, and if this is divided by the square of itself, then basically you just really just divide by it. So that's it is exactly the same as Newton-Raphson if this thing is 0. Oh well. I think it's pretty obvious that it's not going to help. Well, in this case anyway, it doesn't help. Maybe sometimes it does help. No. So this really, in the end, you just want it to be, it should be totally enough to do it once. Sure. Why? Oh, this suddenly takes a lot of extra steps. It's strange. Oh, I think I know why. Yeah, we're just printing 38 digits, which belongs to 128 bit accuracy, but I'm calculating with 256 bits. So half of the digits aren't even visible here. I should probably change it. Yeah, if I keep printing this anyway. So let's print. What the F? Rather, I'm using 38. I probably just should set it here as well to that. How do you get from 256 to, well, rather from 128 to 38, divide by the ln of 2? What is the ln of 2? 2, 2, 2, 2. The ln of 2. It's less than 1. This ain't it. No, it's the log 10 of. Fuck this. It is the log 10 of 10 to the power of 38. Which is then equal to 2 to the power 128. So the 2 to the power position bits. Yeah, so that is position bit times the log 10 of 2. Not the not the ln of 2. The log 10. The log, is this a log 10? I have an ln and a log. I guess this is the log 10. 0.3. What? Okay, 0.3 times 28. Yeah, that's more like it. Age is back. It compiles. Dun, dun, dun. Well, wow. It's taking its time to become stable here. So we have this value. That's weird. So we have this value already there. And then it's just noise, as it were. 28, 29, 31, 32. No idea why this loop stops. I stop in the step 0 or when it's equal to the previous value or the previous value. So because of this one is equal to that one. Okay, so and it compares that one to that one. It's not equal. I think we were lucky that it stopped. not a good stop condition then. Probably should just stop. I'm just gonna add a counter, I think. Although, damn it. If you know 100% certain that it begins with at least 6 digits, then you can just stop after a while. It should triple every time. But you don't know that. Maybe sometimes something is super off. Then it's gonna take a while. In the real code I used a trick that I consider the last calculation to be precise. And then I calculate the relative error in the previous one. And if that relative error is less than a certain value, then we stop. Because we know that that accuracy triples every step. That it is like super sneaky, but it works. Yeah, okay, let's just do that. So we calculate. I'm not doing the previous. I mean, this is attempting to be as precise as possible. While the real code is just trying to be smart and fast. In this case, I do want to be as accurate as possible. It's still a stupid way to do it. Okay, I'm gonna not do it like this. We do away with the previous. Do I even use the previous step? Previous step. Nope, not being used. Remember the current U. Calculate a new U. Now we can calculate the relative error in the previous one. Or even call it previous. The previous relative error is previous absolute relative error. Yeah, and then yeah, just hope that u is not 0. But yeah. Oh, we can do that, yeah. Can do that. Why is it trying to do that? I want to use MPFR apps. Well, not really. I want to use that with König lookup. How do you call it? So the argument is in the namespace, in that namespace, and therefore it should pick this one. Oh, never mind. I know this thing isn't even a template. Never mind. Never mind. That was the other file. Something else that I was working on. Yeah, well, then I could add a namespace here because I think that no, the namespace is at the top, so this should work now. Compile. Yeah, okay, to be expected. I wanted to see the beginning here of this, so. So clearly we reached full accuracy like, well, here already. And that is because we had this accuracy. Even one more. And then the number of digits is tripled. So we don't even need this accuracy. Just totally don't need that. But why not, you know? As soon as we're going over the half or something-ish, or 1/3 actually, but a half. And then the relative error is 6 times 10 to the power minus 46. Really? I guess this is... okay, so if I make this, say, 1e minus 38, or if I want, if theoretically a third of the maximum thing that we reach, So a third of this would be, but yeah, I don't want to do the 3. So let's just do half of that. I'm just going to go, 38 times 2 is 60, 76. So I'm going to do the 38. And then, of course, this variable does not exist anymore here. That is so annoying. Just have to calculate it here. Can't print it then. But that 38 is then, I think, half of this value. Really? I don't think we can put it in here. Can you put a const expression as a variable in an exponent? I don't think so. It should have been possible, but no. I just have to do a const expression standard power. That's standard power is const expression, huh? Oh, I'm not even compiling this with optimization. Maybe I should have moved. Yeah. Can I compare to the double to begin with? It is a double. Hmm. False limit. So boundary limit. What is the best word here? Threshold. That is the word. Relative error threshold. That was not good. Oh, it is good. No, it is not good. Or is it? Damn it. It's not good. I think we need one more. No, we don't. Sorry. this is the previous value. Yeah, this is the previous value, and it doesn't print the actual result. Because I only printed at the top. Printed at the top here, not the bottom. Print at the bottom. Yeah, so because this is already accurate and this one has 3 times as many accuracy, and then whatever it doesn't have as accuracy is can't be helped, I guess. So it's just a good point to stop there. Don't print it at all. This works. So I think this is the one. As you can see, the root is just in the inflection point. So the curvature is even 0 here. And the derivative is also 0. So that's the reason why it doesn't work very well. However, there's more where that came from. Yeah, the derivative is not 0. I mean, it's in the inflection point, but the derivative isn't really 0. So why? Now, it might be that the reason might be that I'm moving the inflection point to the origin before I calculate the root. And then we calculate the root, and then I move it back. But why would that be inaccurate? Can't be. I'm doing a final Haley step on the real root here, on top of everything. So we move it back, and then we do again a Haley step. So it would have to be insanely inaccurate, or Haley is still not working. There's another one. So not really 0. I mean, you can even see that it is not 0, the derivative. It seems that it's, yeah, and the main characteristic so far is that the 0 is the inflection point. I just don't understand why it is so inaccurate. Why would that be? Why would that? Why would the root being the inflection point cause the calculated root to be so inaccurate? Now this again clearly the inflection point. This too. Yeah, also. And this one isn't. Wow, the inflection point is like here. Like totally not the root. This is very interesting because I already detected this case where a local extreme touches the x-axis. That is inaccurate as well. But I should be skipping that now because I'm detecting that that is the case. I'm kind of disappointed that this one pops up. Okay, so the program that I wrote was so I can now just copy this line. Paste it here and get the exact root. It's a 0.45 it has. Wait a minute. There's more of that. This one. Yeah, so this one. That's the best thing that fits in a double. So hardly, so again the last 3 digits. So the offset is, it stops because the offset is larger than 10 steps, where 1 step is just the next double that can be stored. So just the least significant bit is incremented basically. So you do that 11 times, then still not a lot, of course. It means that the last 3 bits are not accurate. 3 or 4 bits. on the 51 bits, right? Want this has 51 bits accuracy, and then we have 3 or 4 bits are not accurate. Yeah, well, that's not much, but the question was why did it not detect that it is of that type? Okay, maybe I can add that as well. Let me copy this again. Put it on Discord. Okay, and then I want to look at the code that detects that. That is part of this random cubics, I suppose. Yep, that would be the special case is true. So apparently you don't get here for this particular case. Let's just do the. Let's add this to the print route, so I know which if it is case 1 or 2 or none of neither. Doesn't really matter, I guess. Need a spacer anyway. Wow, the discriminant is negative. No. Possible. Yeah, let's also draw the thing. And I always call a thing cubic. Why suddenly call it P? It's like literally a cubic. Oh, yeah, that is true. This is not a special case too. I thought I had stored. Okay, that's weird. Oh, okay, never mind then. Print roots. That one. Yep. Yeah, that one. So this one does touch it. And that should be special case 2. Not special case 2. Well, that's interesting. Even I see that this thing does have roots. So that is what is wrong. It's not capable of calculating the roots of this thing. You're like, come on. Bullshit. There's 2. Hmm? Oh, it just prints this. Well, it should not have printed it. This is the real reason. It's just a tiny little bit larger than 1/10. Yeah, that happens. What? Why do I have 2 spaces here? All that effort. Yeah, these must both be less than 0.1. So, make it a half. 0.2 then maybe. Quarter. Nah. The 1/10 is so that the third power of that is 1,000th, which then can be more or less neglected compared to the 100th, so it's just 1 decimal. I don't want to make this larger than 0.1. But apparently it's still bad. It's still, yeah, we'll have to live with it. Okay, let's quit for today. Let's play chess. We go here and I give check and I put my pawn here and he just takes it and I take back. Can't take back, wait a minute, it's nonsense. What is nonsense? I'm not sure it makes sense to put it here though. Why you could I wanted to put it here. I gave away this pawn. I did not take it. Yeah, I don't know why I put the bishop here. That was just stupid. That was just stupid. I want to occupy the center, which means I need to move the pawn here, which means that this becomes weak. I have to put my bishop back. He's gonna play this anyway. Let's put the bishop here. Let's admit a mistake. No, this is a backwards weak pawn. So I want to put my knight over here. Which would be nice. It's not possible. He's just gonna take it. Damn it. If you go here, I'm even 4 moves away from this square. But also here, so that maybe I should just go here. It's a bishop pair. No. Yeah, now it's not a weak pawn anymore. Duh. What's gonna happen with this pawn? He's gonna attack it and then I can't defend it. Yeah, let's do this. Mhm. I also have my bishop pair back. I don't consider it a very good bishop, actually. All those pawns on white. Oh, I gave away my pawn. Never mind. How can I have been this stupid? I had prepared this pawn, and I'm doing this. Too late. Did I just give away this pawn as well? I'm pretty sure I did. You're giving away everything. Nope, not good. Should have played this bishop first. Yeah. Oh shit. You could have given maiden one. I did not see that. Finished. Finished. Yeah, well. I did something stupid. That was already not super good, I thought. Yeah. Playable. Yeah, putting the bishop back, nah. Just develop another piece. Always better. That was bad. That was seriously bad. Block my own bishop. Yeah, I could have attacked this pawn. Keep the initiative, man. Kind of has to move it, and then we can go back. Draw his position. I did something else very wrong here. I gave away a pawn. Here I could defend the pawn. Just didn't see I could take it. So stupid. -3, give another pawn. Yeah, horrible. I could have taken the queen with a draw. How is that a draw? Oh, because I win this pawn back afterwards. Oh, yeah. Yeah, indeed. Completely missed that fork. Completely missed that fork. And again, and still it didn't do it. It's really just the problem here is clearly I can't play chess. That is like the problem. Yeah, I just had nothing. Completely lost. But he did miss a maiden one. Let's see that one. Maiden one, rook f1, and he didn't see it. No. Gonna play one more and then I go to bed. Just one more. Promise. No. The pain, the pain. I so fucked up in the end. I am -1. What should I have done here? Pin the knight. Develop a bishop, pin the knight. Why? Oh my god, yeah. I'm totally won here. And that's what I did. No, I didn't. I did it one move later. Yeah, it's a fork. It's a fork on 2 pawns. How are you gonna defend that? Not. Cannot defend it. I just win a pawn. Indeed. So here I did not see that. And then I thought I had something. It's a -1.4. That's what I did. It's again -2.5. -2. And here it was stupid. I gave away that pawn. Yeah, that's not good. I thought I had a fork here, but if I do the fork, I'll lose my center pawn. So that should have played the bishop or something. Or just leave the knight and put the bishop here. Oh, that's also attacking something. Very nice. Yeah, definitely. Very nice. Oh, castle long? Yeah, it's just completely winning here. But now I give everything away, and then he gives everything back. Except that yeah. No, still -0.7. We'll make it a draw again, but he doesn't see that. The castle short. I really wanted to draw at this point. -3. Wow. I did see that one. -3. Push the pawn. I did not push the pawn. I took here. Immediately pushing the pawn. I thought the problem with this is that he just pushes the pawn. And then my knight is attacked and I can't take here because, well, I can, but then I take 2 things in a row. Oh, with check, yeah, of course. So if he pushes, I just take. I thought my bishop is not defended. But he can't push because I take, and even if he takes back, I take again. That wins a whole piece. Yeah, then this move is just, hello. Incoming. Not to mention that. The knight could go here, but I just take here. Queen moves, I take here for check. It's just wins piece. Okay, this also wins a piece. It's all that one. -2. Scary cat move. -2.5. Very good. Minus 2.5. Just exchange queens and you have a quality more? No. Oh, yeah, that was losing. So that was a losing move. Well, not even that bad. Just missed completely that I made a hole here. Who would have known that a hole would appear here if I played this ball? Well, I just was a bit tired of my queen having to defend this point. I wanted to go here and stuff. So they do this and then they go there. Not. Also gives everything away. Could play back. And this doesn't work because... Oh, the rook here. It takes two pieces at once. Okay, bedtime.